All right, last section for this unit is syllogistic arguments. So this goes full circle back to our first day of class when we had section 3.1, that long, boring section. And the first thing, one of the first things we talked about was the negation and negating quantified statements. Okay. And in case you don't remember what the quantified statements are things that start with either the word all or no or none or some. Those are the three quantified statements. And we talked about negating them. And just as an aside, please review that before the test. Okay, I'm going to throw two quantified statements that you have to negate on the test. So just please make sure that you remember how to do that, so you can get those points. Okay, so here what we're going to do is we're going to determine if an argument that contains either an all or a none or a some statement, can I determine if this is valid or invalid? And so what we're going to do is we are going to use some diagrams by a famous mathematician named Leonhard Euler. Okay, it looks like Euler, but it's Euler. He was German. He did a lot of fun things. If you take MGF 1107, he started a whole new branch of math that's a lot of fun. It's called graph theory. It's basically just going around points on a graph. It's my favorite unit in that class. So come join me next fall when we do that. Anyway, that's an aside. So what we're going to do real quick is we're just going to see an example of each of these quantified statements and how we're going to draw circles. We're going to draw a circle to represent each of the things, and we're going to see how they interact with each other. So first one, all dogs are brown. Okay, so whether that's true or not true, that's not what we're trying to determine. We're just trying to draw circles that represent this relationship. So I need a circle for dogs and I need a circle for brown things. Okay, so I'm going to draw those in a minute. When you have an all statement represents that one circle is going to be inside another. So for instance, I'm going to take one circle and I'm going to put it inside the other circle. That's saying all of one of the things are another. So in this case, which one's going to be the dog circle? Which is the dog circle going to be the bigger one, or is the dog circle going to be the one that's inside the bigger one? Okay, so if I put the dog circle out here, I don't have a pencil. Don't write this down. If I put the dog circle out here and then I put brown things right here. So what this is saying is that I can have dogs that are other colors, right? I can have red dogs, I can have green dogs. But this statement, whether we agree with it or not, says all dogs are brown. Okay, so what I'm going to do, and so that was a good hypothesis. I appreciate you making it. What we're going to do here is we're going to reverse the order that you said, and I'm going to put the dog's circle inside the brown circle. So this now says if you have a dog and it's in that circle, it has to be brown because that's what that statement said. So in general, whenever you see an all statement, whatever comes right after the word all, that's going to be the smaller circle. Okay, that's going to be the one that's inside. The next one. No dogs are brown. So again, not concerned whether that's true or not. But if I have a circle for dogs and a circle for brown things, if no dogs are brown, how do you think those two circles are going to interact with each other? Yeah, they're going to be separate. So I'm just going to put one. It doesn't matter where you put them. All that matters is that they are going to be separate. So I have dogs, I have brown things, and no dogs are brown. So those circles don't interact at all. So in general, whenever you see a no statement, you're going to write the two circles apart from each other. Last but not least, some dogs are brown. How do you think these circles are going to interact? Yeah, like it's not maybe quite the opposite of all, because the opposite of all, I think, would be the none. That's a good thought. But so again, if I did that, that would be saying, so if I did this, The reason that this would not be the way to do it, that is a really good hypothesis. But now what has happened is unintentionally, what you've done is you've said all brown things are dogs. Okay, so that's not what we're communicating. We're communicating that some dogs are brown and there's going to be other brown things. There's going to be dogs of other colors. Okay, so we're locked in. So what was said right behind you, though, is going to be how we're going to do these circles. We're going to have my dog circle right here, and then I'm going to have my brown circle right here, and they have that overlap. And this overlap right here, those are the some dogs that are brown, and where they don't overlap, these are the some dogs that are not brown. So you've kind of said two things there with both. So I just wanted to give an example of what you're going to do when you see these quantified statements. An all statement is always going to be one circle completely inside the other. The no statement is going to be two completely separate circles. And then a sum statement is going to be two circles overlapping. And this is how we're going to determine if a statement is valid or not. So for instance, now for the rest of what we're going to do here is just practicing this skill. Okay, so example 1 says all college courses are fun. It then says MGF 1106 is a college course. And so then therefore, do I have to come to this conclusion? Is this a valid conclusion? MGF 1106 is fun. So once again, just like last time, the two statements above the therefore, these are the premises. That's what I'm going to draw, is my premises. And then this last thing, this is my conclusion. And what we're going to look is, when I do my drawing of my premises, do I have to come to this conclusion? Is this the only conclusion that I can possibly make given the drawing of the premises that I have? Okay, so let's see. All college courses are fun. I need two circles. It's an all statement, right? So all statement means I have one circle inside of another circle, just like that. So which one's going to be the one that's inside? Perfect. I'm just going to abbreviate. Just use the word college. Yes, because all college courses are fun, so there's other fun things, but we know that if you're in a college course, you must be having the time of your life. It's fun according to that statement. Okay, so remember what comes immediately after the all is always going to be the smaller circle. So the college courses is the smaller circle. So MGF 1106, now this is just one particular item. It doesn't have a quantifier. I don't need to draw a big circle. I just need to put this element in there somewhere. Where am I going to put MGF 1106? It's a college course, right? So it has to go in this circle right here. I'm just going to draw a little X, and I'm just going to label it the MGF. Again, just to save a little room, because I didn't really make the boxes probably as big as I should have. I'm just going to abbreviate. Before we go to the conclusion, does everyone see why we drew that way? Is there any other way I could have drawn that according to the information that I was given? No, because the college circle has to be inside the fun circle. We know that. And then the MGF 1106 has to be inside the college. I can't put MGF 1106 out here because then I'm saying it's not a college course, and then it's not fun. So here's the question. Here's the conclusion. According to the picture that I've drawn, according to this, does it have to be true that MGF 1106 is fun? Is MGF 1106 in the fun circle? Yeah. Yes, it is. So this is a valid argument. Okay, we're going to make a few mistakes as we go along the way, but it's all in our effort to learn. So here's what I would like you to do. Example 2, I want you to go ahead and draw the diagram for that, and then see is the conclusion one that you have to come to. Okay, so let's give this a try. Okay, and then if you got any questions, let me know. So the first statement is a sum statement. So that means I'm going to have two circles that overlap each other. So some nurses work in pediatrics. So there's my sum statement. Then we're told Lisa works in pediatrics. Now, here's the thing. Don't assume anything about Lisa other than she works in pediatrics. So can I put Lisa, if she works in pediatrics, can I put Lisa right here? Is that inside the pediatric circle? Yes, but also, and I think this is what some of you were just responding to, could I put Lisa here? Yes, she could be in either place, right? Does either place violate the premises that I was given? Okay, so here's the question. Do I have to come to this conclusion? Do I have to assume that Lisa is a nurse? No, she could be if I put her right here, but she also might not be, might be a doctor, okay, might be something else. So because there's a choice here, because there's two ways I can do this drawing, that's what makes this an invalid argument, okay, because there's more than one conclusion that we could come to. We're just not given enough information to know what Lisa's role is. All right, I'm going to flip the page. Just going to learn by getting more experience. So we've got a few more that we're going to do. So the next one, try this one. All right, so I'm going to get started on this one. My first statement is an all statement. All ballerinas are athletic. So I'm going to draw one circle inside of the other for my all statement. Which circle is going to be the smaller circle? Okay, that is the one that's right next to the all statement. So, okay, so all ballerinas are athletic. That's fantastic. Good work so far. Then we are told Russell is athletic. Okay, so Russell has to be in the athletic circle. So can Russell be right here? Does that meet the criteria? Could Russell be in here? That's still Russell being athletic. So do I have to come to this conclusion? Is this the only conclusion is that Russell is a ballerina? No. Russell could be, but Russell also could not be. So again, because there is because there's more than one way I could draw this drawing, that is an invalid argument. I'm going to do the next one with you, because now instead of being given in my second premise just a specific instance, so we were given Russell is athletic, we were told Lisa works in pediatrics, we were told MGF 1106. This second one, in this next one, the second premise is also going to be a quantified statement. So first statement, all Earth people have two arms. Okay. Great, kind of a weird statement, but that's okay. So which one's going to be the inside circle? Okay, so I'm just going to use the letter E just so that I don't mess up this drawing too much. And then I'm going to put the number 2 for two arms like that. So all Earth people have two arms. So far, are we so good? We're doing all right. Okay, so the next statement has another all. It says all people with two arms can fly. So I need a new circle and I know I need a new circle because it's an all statement. So I need a circle for things that can fly. So the question is this. Is the things that can fly circle, is it going to go inside the two circle or outside the two circle? Why'd you say outside? Yes, because people, okay, the people with two arms comes right after the all. So that means the people with two arms, remember I told you whatever comes right after the all is the smaller circle always. So I'm going to put the fly circle right out there. So now, looking at that drawing, there's no other way I could have drawn the flying circle. It has to go around the two arms circle. So therefore, do I have to come to the conclusion that all Earth people can fly? Where's my Earth people circle? It's in the middle. Is it completely inside the fly circle? Yes, so this represents my Earth people is completely inside this circle. That is this statement right here. All Earth people can fly. So that makes this a valid argument. There's no way for the Earth circle to leak out because it has to be completely within the two arm circle. And then the two circle has to be completely within the fly circle. So there's no way that any of the Earth people circle can go to the outside. So it has to be valid. Now, that's not always going to be the case, so that's why we got to draw the drawing. Here's one for you, example 5 of doing another set of circles, just so that you get to practice your drawing skills. Okay, so my first statement is all dolphins are mammals. So here is my two circles for all dolphins are mammals. Which one's going to be the smaller circle, the dolphins or the mammals? Okay, the dolphins. Okay, all dolphins are mammals. So just before we go on to the next one, will I find any dolphins out here in the box? Nope. Will I find any dolphins out here between the two circles? Nope, they're all in there. Okay, so great. So now I need another circle. All mammals are vertebrates. So my vertebrate circle, is it going to be bigger than the mammal circle or is it going to be smaller than the mammals circle? Okay, it's going to be bigger. Yep, because in that all statement, the mammals has to be the smaller one. So this is the vertebrates. Okay, so there's no other way I can draw that because the vertebrate circle has to go around. It doesn't go through the circle. There's no other options. So therefore, does that diagram represent that all dolphins are vertebrates? Yes, it does. It's a valid argument. Okay, fantastic. Just a couple more. So give example 6 a try, see what conclusion you can come to, and then we'll go through it together. All right, so on this one, it first starts off saying some caterpillars have fur. So I'm going to draw circles that overlap. This is my caterpillars. I'll just abbreviate that CP. Here are my things that have fur. So then the next statement says all things with fur are mammals. So I need a new circle. I need a mammal circle. And what is that mammal circle going to go around? The fur circle. It could go around both. It doesn't have to go through both. I'm just going to draw it like this, but if you drew it all the way around, it's not going to affect anything. So this is my mammal circle. Oops, this pen's out of ink. So there's my mammal circle. So given that, can I come to the conclusion that some caterpillars are mammals? Yes, that is going to be good. Even if you drew the circle all the way around, okay, even if all the caterpillars are in the mammal circle, that also implies that some caterpillars there's some group of caterpillars. So this is a valid argument right here. All right, we've just got two more. Give example 7 a try, please. Okay, so this one starts off with all marigolds are annuals. So it's an all statement. So whether or not I know what a marigold is or an annual, I can draw this. So all marigolds are annuals. So since marigold is right next to the all statement, I'm going to put those right there. And then the annuals, the bigger. Now it says some tulips are annuals. So I'm going to draw a tulip circle. Okay, so here goes. I am only told that the tulips are annuals. So I'm just going to draw, I can draw it like this. Here's my tulip circle. Could the tulip circle intersect with the marigold circle? It could. Does it have to? No, it doesn't, as long as it goes through the annual circle. So do I have to come to this conclusion? Do some tulips have to be marigolds? No, it could be, but we're not given enough information. So this is an invalid argument right there. One more. Last one, example 8, then if you have any questions, please ask them. That way we can all be good and settled and feeling secure going into Thursday. Okay, so it says all Call of Duty players are students. So it's an all statement. And so the Call of Duty is going to go inside and then students will go outside. This one reverts back to the second statement is not a quantified statement. The second one is just a particular. We've got Joel. And so Joel is going to go where? Yep, Joel is going to go in here. Is it possible to put Joel out here? If I put Joel out here, is he a Call of Duty player? No, so he has to go in that circle. Okay, so just making sure I'm illustrating why we're going to say what we're going to say in just a minute. Joel has to go in that circle. He can't go anywhere else. So do I have to then come to the conclusion that Joel is a student? Yes, he is. Okay, so this is a valid argument. So that is the idea of a syllogistic argument. It's just drawing some circles and seeing if I have to come to that conclusion.